Hi, welcome to the VSERP Practice Examples video. So in this video I'm going to go over the 5 steps that are used to determine the shapes of molecules, and I'll also go over bond angles. Okay, so the very first step in trying to determine the electron domain geometry or the molecular geometry from a chemical formula is to draw the Lewis dot structure. So when drawing the Lewis dot structure, first thing we do is we determine the total number of valence electrons. This molecule is Hcn. Hydrogen is in group 1, so the hydrogen has 1 valence electron. Carbon is in group 14, it has 4 valence electrons. And nitrogen is in group 15, it has 5 valence electrons. Remember, the valence electrons go 1, 2, skip the middle, 3, 4, 5, 6, 7, 8, with the exception of helium, which only has 2. All right, so we've got a total here of 10 valence electrons. All right, my next step is to figure out what's my central atom and draw my skeletal structure. Now, the central atom will be the one that's the least electronegative, with the exception of hydrogen, because hydrogen cannot go in the center since it can only have 1 bond. So hydrogen always is a terminal atom. So in terms of what we have left, carbon and nitrogen, carbon is to the left of nitrogen, so carbon is the least electronegative, and it goes in the center. Now typically the least electronegative one is the first atom that's written, but since it's hydrogen, it can't be that one. So I draw carbon in the center, and then I attach the other atoms with single bonds. So now the next step is to determine how many valence electrons do I need to give every atom that needs an octet an octet. Now remember, hydrogen only wants to form 1 bond, so hydrogen's good, so I just need to check the carbon and nitrogen. Alright, so an octet means 8 electrons around it. Carbon right now has 2, 4, because each bond has 2 electrons, so carbon right now has 4 electrons around it. To get to 8, I need 4 more. And nitrogen has 2 right now. To get to 8, I need 2, 4, 6, so 6 more. That means I need a total of 10 electrons. All right, but in my structure, how much do I have left? So I start off with 10 and I use 2, 4. So that means I only have 6 remaining. So what I have is less than what I need. So when that's the case, then I know I'm going to need to do some double or triple bonds. And since the difference between the two, how much I need, 10, and how much I have, 6, is 4, that means I'll probably do a triple bond. And I'm going to put that triple bond between the carbon and the nitrogen, because remember, hydrogen is already good. So the only ones that need to do extra sharing are the carbon and nitrogen. So I got my triple bond in there, and carbon looks good, it has its octet, but nitrogen needs a lone pair. Now let's go ahead and make sure we use the 10 electrons we have. 2, 4, 6, 8, 10. All right, I used the 10 valence electrons. Okay, so that's step 1, just the Lewis dot structure. All right, now step 2. We're going to now count the number of electron domains around the central atom, and number of lone pairs. So we just focus on the central atom here. Carbon is that central atom. Electron domains are the spaces occupied by lone pairs or bonds. So that's 1, 2 electron domains around that central atom. Notice how for the triple bond I counted as 1 electron domain, even though there are 3 bonds there, because it's the same space. Whether there was 1 bond, 2 bonds, or 3 bonds here, it's still the same space. All right, so 2 electron domains, and then there are no lone pairs on the central atom. Okay, so now my next step is to determine my electron domain geometry and molecular geometry. All right, and this is where that chart comes in. If you have 2 electron domains and 0 lone pairs, then you're, for electron domain geometry, back up, it's just determined by the number of electron domains. So we have 2 electron domains, the electron domain geometry is linear. All right, now for the molecular geometry, that depends on the electron domains and lone pairs. So if you have 2 electron domains and 0 lone pairs, the molecular geometry is linear. Okay, let's do our next example. H2O. So same thing, we're going to start with the Lewis dot structure. Hydrogen, each hydrogen has 1 valence electron because it's in group 1. So that's a total of 2 there. And then oxygen has 6 because it's in group 16. So I have a total of 8 valence electrons. My central atom here is going to be oxygen, since hydrogen cannot be a central atom and only wants to form 1 bond. So I put oxygen in the middle, and I put my hydrogens. Now I've used up 4 electrons out of the 8 I had. That means I have 4 more remaining, and I need 4 for the oxygen to give it a lone, an octet. So I just throw my lone pairs on there. Okay. Now we're going to do our counting our electron domains and lone pairs around the central atom. So again, we're just focusing on the central atom. We don't care about the terminal ones. So around oxygen, the number of electron domains: 1, 2, 3, 4. Notice how I counted the bonds and the lone pairs. So your next electron domains are the spaces occupied by the bonds and lone pairs around the central atom. So that's 4 electron domains. All right, 2 of those electron domains are lone pairs. Okay. So now we're going to use that to get our electron domain geometry and molecular geometry. So we have 4 electron domains that I'm going to use for my electron domain geometry. So if you have 4 electron domains, which are here, that corresponds to tetrahedral. Okay. So 4 electron domains, electron domain geometry, which is in that second column, is tetrahedral. Now to figure out my molecular geometry, I need to know how many lone pairs I have. I have 2 lone pairs, so 4 electron domain, 2 lone pairs. That gives you angular or bent. Okay. And let's go on to our next one. In the end, we'll go over the bond angles. So for our next one here, CCl2O, carbon is in group 14, so it has 4 valence electrons. Each chlorine is in group 17, so 7 valence electrons. And then oxygen has 6. So we have a total here of 24 valence electrons. All right, my central atom is going to be carbon. It's the one that's written first, which is typically the central one, and it's the least electronegative. So I'm going to go ahead and put, now the arrangement doesn't really matter. I'm putting carbon in the middle, so that's the part that counts, and then everything else, the 2 chlorines and the oxygen, are connected by single bonds. Now I used up 2, 4, 6 electrons so far out of my 24, so that means I have 18 remaining. Let's see how many I need. Each chlorine needs 6, and the oxygen also needs 6, and the carbon needs 2. So that means I need 20, but I only have 18 remaining of the 24 since I used 6 of my 24. So that means I'm definitely going to have a double bond, and that double bond is going to go between the carbon and the oxygen. So chlorine, which is in group 17, they oftentimes don't have double bond elements in group 17, but oxygen, nitrogens do. So that's why I'm going to put my double bond there. And then I'm going to arrange my remaining valence electrons to give everything an octet. All right, let's make sure we did this correctly, that we used up 24 valence electrons, no more, no less. So 2, 4, 6, 8 from the bonds, 10, 12, 14, 16, 18, 20, 22, 24. Okay, great. All right, so this is the Lewis dot structure. Now, next step is to determine the number of electron domains. So again, you focus on the central atom. Here, 1, 2, 3. Notice that again, the double bond counts as 1. So there's 3 electron domains here. And again, on the central atom only, are there any lone pairs? Nope. There are lone pairs on the terminal atoms, but they don't count and they don't impact the shape. Okay. So we have 3 electron domains, 0 lone pairs. All right, our handy dandy chart here. So if you have 3 electron domains, the electron domain geometry would be trigonal planar. All right, what about the molecular geometry? So now for that, we need to figure out the number of lone pairs as well. So 3 electron domain, 0 lone pairs. So 3 electron domains, 0 lone pairs. That's trigonal planar as well. And one thing you will notice is that whenever the number of lone pairs is 0, the electron domain geometry and molecular geometry are going to be the same thing. Because in the molecular geometry, you're ignoring lone pairs, but if you have no lone pairs to ignore, then you're going to have the same same geometry as the electron domain geometry. All right, last two. NH3. Nitrogen is in group 15. It has 5 valence electrons. So again, we're starting with a Lewis dot structure. We're getting our total number of valence electrons. Each hydrogen has 1 valence electron. That's a total of 8. Okay, so we have 8 valence electrons. All right, the one that's going to go in the center is nitrogen, because hydrogens cannot go in the center. So I make my skeletal structure by attaching all the other atoms to my central atom with single bonds. All right, now I've used up 2, 4, 6 electrons to make the skeletal structure. I start off with 8, so that means I have 2 remaining, and I need 2 to give that nitrogen an octet. Okay, so this is my Lewis dot structure. Now, let's go ahead now and count our number of electron domains. So again, focusing on the central atom. 1, 2, 3, 4. We have 4 electron domains. Remember, I'm counting spaces occupied by bonds and lone pairs. And one of those electron domains is a lone pair, so 1 lone pair. Okay, electron domain geometry for that. If you have 4 electron domains, then the electron domain geometry will be tetrahedral. So remember, for electron domain geometry, you just figure out how many electron domains you have. So tetrahedral. Now, what if one of them is a lone pair? Then 4 electron domains, 1 lone pair is trigonal pyramidal. Okay, so 4 electron domains, 1 lone pair. Molecular geometry is trigonal pyramidal. Okay. Last example, CH4. Okay, so carbons in group 14, it has 4 valence electrons, and each hydrogen has 1. That means we have a total of 8 valence electrons here as well. We have carbon, and I attach all my hydrogens. All right, this one's pretty simple. So I used up all of my 8 valence electrons, and carbon has its octet, and hydrogen's good with its 1 bond. So this is our Lewis dot structure. Now we're going to go ahead and count our electron domains. 1, 2, 3, 4. 4 around the central atom. 0 of them are lone pairs, so none of them are lone pairs. And whenever you have 4 electron domains, the electron domain geometry is tetrahedral. If you want to see that in the chart, 4 electron domains is tetrahedral. And then finally, for the molecular geometry, if you have 0 lone pairs, the molecular geometry will be the same as the electron domain geometry. So I don't even need to look at the chart here. All right, last thing we're going to discuss are the bond angles. So I just want to show you the shapes of all of these examples that we did. So starting off Hcn Hydrogen Cyanide. This is a model of hydrogen cyanide. Blue is my nitrogen, black is the carbon, and white is the hydrogen atom. This is a linear structure. You can see the structure shaped like a line. And the bond angle in a line is 180 degrees. So the bond angle here will be 180 degrees. okay, because it's shaped like a line. When we say bond angle, what we're looking at are three atoms that are connected. What is the angle between those atoms? All right, now let's take a look at water. Here is water. So this is the model for water. Notice how the Lewis dot structure, it looks like it's linear. So you would think, oh, it's linear, it's going to have a bond angle of 180. It doesn't. So an angular shape will definitely have a bond angle of less than 180. But what's the actual bond angle? And this is where the electron domain geometry comes in hand or handy. So the electron domain geometry here is tetrahedral. And when you have 4 electron domains around a central atom, they're going to arrange themselves so they're farthest apart. And in order for them to be farthest apart, the angle between the electron domains are going to be about 109.5 degrees. However, if you have a lone pair, remember lone pairs have a greater repulsion. So they're going to squeeze those bonds in closer than 109.5. Okay? So when you have one lone pair, it's going to be slightly less than 109.5, like maybe 107 or so. And then when you have 2 lone pairs, it squeezes it even more. So maybe it's closer to 105. So this bond angle is going to be less than 109.5. degrees. And remember, we get that again from the fact that tetrahedrals have a bond angle of 109.5, but since you have 2 lone pairs around that central atom, those lone pairs have very great strong repulsion. They're going to push those bonds in closer. That bond angle is going to be less than 109.5. See the bond getting smaller. All right, next example that we're going to look at is, here we have, this is called Phosgene, by the way, this molecule. All right, so let me turn it this way. So the red is the oxygen, the greens are the chlorines, and the carbon is in the middle. And in this structure, this is a trigonal planar structure, so they'll sort of shape like a flat triangle. So the bond angles for trigonal planar, you think of a circle. If you divide a circle into 3 parts, what do you think the bond angle is going to be? 120. So a circle is 360 divided into 3 parts, it's 120 degrees. And all that, by the way, is in the chart as well. So you can see here for trigonal planar, has a bond angle of 120. Okay. Next one, NH3. Here's NH3. So this is a tetrahedron. I'm going to put it off to the side so you can see it a little bit. It looks like a tripod, but instead of the top of it being another bond, the top of the trigonal pyramidal is the central atom, because you have this lone pair here. And so again, the electron domain geometry, this is where it comes in hand. Tetrahedrals have a bond angle of 109.5. But since you have a lone pair here, it's going to push these bonds in closer together. So the bond angle is going to be less than 109.5 because they're being pushed in closer together due to that lone pair. And this is NH3. This is what NH3 looks like. Okay, a little tripod. All right, final structure is tetrahedron CH4. So if you have a tetrahedral structure like CH4, their bond angles are 109.5 degrees. Okay, you can see that again, it looks like a tripod. So they both sort of look like a tripod, but here the top of the tripod is comes from a bond, and here the top is just the central atom. So the trigonal pyramidal structure is shorter than a tetrahedral. Okay. All right, I hope you found this video helpful. There are some practice problems. You're going to do the same thing in your practice problems. Have a quality day.